We said that a rational function was the quotient of polynomials. And we said if you first look for the degree of the numerator is greater than or equal to the degree of the denominator, you start by long dividing, and sometimes that just does the trick. Like after you long divide, you just be done with the problem. But then sometimes you'll have a new fraction, which where the numerator is less the degree of the numerator is less the degree of the denominator, and this requires this technique of partial fractions, and we did this example last time. We finished that one up. So let's work on another one. And so again, in order to use the partial fractions technique, there's two criteria that you're looking for. So the first is it's a rational function with the degree of the numerator less than the greater than no, less than the degree of the denominator. Sorry, less than the degree of the denominator. Okay, and then the second criteria to use this technique is that the denominator can be factored. If you can't factor the denominator, you can't split it up into partial fractions. Okay, you have to have denominator is factorable. So those are our two criteria for this technique of partial fractions. So let's see. Do we have a rational function with the degree of the numerator less than the degree of the denominator? Yes or no? Degree 2 in the top. What's the degree of the bottom?
3.
It's 3 because we got an x, and then this will give us an x squared, so we'll have an x cubed term. So check. We got 2 in the top, degree of 3 in the bottom. All right, the denominator is factorable. Is that denominator factorable? Well, of course, it's already factored. Okay, so it's already in factored form. So there's nothing to do, and that is factored form. Okay, so the different one about this example is that we've got x minus 3 times x minus 2 squared. So what we have to do for that is we have to consider every possible denominator that would contribute to this being the common denominator. So it's not just x minus 3 and x minus 2 squared, although those are possibilities. So we're going to x minus 3 is a possibility, and x minus 2 squared is a possibility. But then there's another possibility that these two don't take into account. Does anybody know what that would be?
Is it x squared plus 1?
No, because these are going to be factors in the denominator.
Mm-hmm.
So what's a factor in the denominator that's not covered by these two that we have here? So I think someone said just a single x minus 2. So if you had a fraction with just a single x minus 2, that would also apply to this common denominator. All right, so we're gonna figure out what our constants are. Say a, b, and c. So for these possible factors of the denominator, x minus 3, x minus 2 squared, x minus 2, and I'm gonna put the x minus 2 first, if that's okay. And so now we got to figure out what the a, b, and c need to be so that when we add these fractions, we get this fraction, right? So we need the sum of these fractions to be the same as this, right? And so this is all about the common denominator, right? So we know to make the common denominator here, what do we need to multiply top and bottom by here to make the common denominator?
X minus 2 squared.
Yeah, so we're missing, well, we got the x minus 3, but we don't have the x minus 2 squared, so we'll multiply that top and bottom. But as we saw last time, all we really care about is the top, so I'm just going to write the top. Okay, and then for this one, what do we need to multiply top and bottom by to achieve the common denominator? So we have one x minus 2, so we need x minus 3, but then also another x minus 2, right? Because the common denominator has x minus 2 squared. So now if I multiply top and bottom by x minus 3, x minus 2, I got my common denominator. Finally, what am I going to multiply top and bottom by here?
-3.
Just x minus 3. Okay. So I could also write, the common denominator, which is this. Because that's where this comes from. Once I multiply this by x minus 2 squared times x minus 3, that gives me the common denominator. X minus 2 times that gives me the common denominator, etc. But for the bulk of solving the problem, we don't need that. Okay, so we don't need that, so I'm just going to erase it. It's now ready to go. So we know that when you add fractions with the common denominator, you just add the numerators. Okay, and so now when we add these numerators, what do we need the sum of these numerators to be?
X squared plus 1.
Right. So now this is going to be the numerator when we add these fractions. It needs to be the x squared plus 1. So we're going to expand this out. Here we go. Ax squared minus 4ax plus 4a is that first one, and then plus bx squared. It's going to be minus 5bx plus 6b. Okay, and then plus cx minus 3c. And we said that has to equal x squared, and let's write plus 0x plus 1. Are we good so far? Does this make sense? Okay, so then I've got my coefficient of x squared is 1. So all my x, when I add my x squared terms together, my coefficient needs to be 1, so I just think that's just a plus b, right? So ax squared plus bx squared has to be 1x squared, so a plus b has to equal 1. Good so far? All right, now my x term. So my x term is 0. So what do I got? Minus 4ax, minus 5bx, and plus cx. So we got minus 4a, minus 5b, plus c equals, that equals 0. Okay, and then finally, constant terms. Plus 4a, plus 6b, minus 3c, that all has to equal what? That has to equal 1, our constant over here. So 4a plus 6b minus 3c equals 1. So now, this time we have 3 equations and 3 variables. But the point is the same. Have I done everything correctly here? Have I made a mistake, computation or algebra mistake that anyone sees? Just don't want to keep going if I might have made a mistake. Plus 6, that looks good. So if you see an error, please speak up immediately so I don't have to backtrack too much. But I think everything's good. All right, so again, you can use any method that you want to solve this system. So like at some point in your math career, you did systems of equations, and there's elimination, substitution, matrix methods. So there's no right way or required way. But when you look at a certain system, sometimes one of these will stick out as being kind of easier than the other. Let it be more efficient. But I notice that I have a plus b equals 1. So what I'm thinking is, if I could eliminate c from these 2 equations, then I'd have another equation of a and b that I can combine with this one. So how would I eliminate c? So to eliminate c, it looks like I can multiply this by 3. then I'd have plus 3c, and I could add and it'd be 0. All right, so negative 12a plus 4a looks like negative 8a. Negative 15b plus 6b looks like negative 9b. 3c minus 3c is 0. Equals 1. So now I've got the a plus b equals 1. And I got minus 8a minus 9b equals 1 as well. And so now just to change it up here, let's use substitution, which is where I could solve for either a or b in this equation. So we'll solve for b. So this says that b equals 1 minus a. And then I can come along and take that and plug it in for b here, and then solve for a. So it would be minus 8a minus 9 times 1 minus a equals 1. Okay, if you got a question, just speak out. But so now simplifying this, I got minus 9a and then looks like or minus 8a and plus 9a, which is a, equals 1 plus 9 is 10. Minus 8a plus 9a is 1a. And then 1 on this side. I'm going to add 9 to both sides. So I think that's right. And then that would make b, from this equation, negative 9. Okay. Correct me if I make a mistake. And then we could use, say, this equation to get my c. So from this equation, it would be negative 40, because I plugged 10 in for a, and then plus 45, because I plugged negative 9 in for b, plus c equals 0. So this makes, this is positive 5. Over here would be negative 5. Okay, I'll stop for corrections or questions.
Professor?
Yeah.
How do you get minus 9b?
For b?
Yeah, minus 9b.
Oh, minus 9b? This one?
Yeah. Mm-hmm.
3 times negative 5 is negative 15. Negative 15 plus 6 is negative 9.
Oh, okay.
So I'm doing 2 steps here. I'm multiplying the 3 in and then adding it vertically. Other questions?
I have a quick question. How did you get the 1x squared plus 0x plus 1?
That's the numerator. So this, when we add together, these are the numerators of our fractions. When we add them together, we need to get the numerator that we have.
Okay, that makes sense.
Yeah.
Thank you.
Yeah. Other questions?
I'm confused on like the first part. I understand the rest. I don't get why you had that middle x minus 2 at the very beginning.
Because that's a possible fraction that would also be in this common denominator that's not covered by these two. So we need to consider all possibilities for fractions that have this as the common denominator. So we would need all powers of x minus 2. If there's multiple powers of x minus 2, every individual power up to the maximum power could also be denominators that if you added these together could get this fraction. And we see that it indeed needed that. See? I actually got b to be something. So in order to add these fractions together and get this, you need a fraction that has an x minus 2 in the denominator, which you see by the fact that we got b is non-zero.
Because I thought in the beginning that we were just breaking it up and like not thinking, just like breaking it up. So
yeah, so we never are not thinking in math class.
No,
so but do you understand what I'm saying? Like if you added fractions together with this common denominator, there's the possibility that you would have a fraction like this. And we proved that it was true. We needed it. We needed negative 9 over x minus 2 as part of the sum to get this fraction.
So how do I think of like what the possibilities are?
All
like,
powers, right? If you have multiple powers, you're going to
Okay.
include all powers up to the maximum power.
and that's it?
Mhm.
Oh, okay.
Other questions? All right, so we're ready to rewrite it now. So it's going to be a was our 10. So now we're ready to write the integral. 10 over x minus 3 plus a negative 9 over x minus 2 plus negative 5 over x minus 2 squared. First, so we got 3 antiderivatives now to do. What's this antiderivative here? 10 times
Natural log x minus 3.
natural log.
Oh, blue.
This one is minus 2 times natural log. Why? Because this is to the first power in the denominator. So is this one natural log? Do I do natural log for this? Natural log of x minus 2 squared?
No.
No. So this is power rule now, right? The only time you do natural log is if it's to the first power in the denominator or to the negative 1. Now this is power rule, so we're going to raise the power. So it's going to be x minus 2 to the negative 1. And thinking about the derivative, the negative can be this negative right here, so then I just need positive 5. So negative 1 times 5 is the negative 5 over x minus 2 squared. So here's our closed form accumulation function. All possible, right? Starting at any value of a for this open form. So this is the open form net accumulation, all open form net accumulation functions with this as the rate, and this is all closed form net accumulation functions with this as the rate. Questions?
Just to clarify,
Yeah.
you put the positive sign because the negative will
Yeah, just take the derivative.
Awesome. Thank
Yeah,
you.
if you take the derivative, you'll get exactly that.
Thank you.
Yeah, sure.
I have a question about like when you took the coefficients and made the 3 equations.
Uh-huh.
Why didn't you include like the x squared and x's when you were?
Because we're just solving for the coefficients. So I could have. I'd have ax squared plus bx squared equals x squared.
Mm-hmm.
But then we're trying to get the coefficients, so then those would go away, right? So we can divide both sides by x squared, and they'd be gone, and then it cleans it up. So we're just focusing on the coefficients.
Oh, okay.
Yeah, I mean our goal is to get the a, b, and c. So as soon as we can get rid of the x's to make it easier to work on, we want to do that. Did that answer it?
Yes, thank you.
Okay, cool. All right, let's try one more example. So now, something I didn't mention here, because we had, so this a, b, and c, these are linear terms, or constant terms, right? Constant terms. And the reason that we have constant terms, that we assume constant terms, is because we have one power greater in the denominator. So x to the first, x to the first. This is still considered x to the first because it's a linear term to a power, but it's still a linear term, so to the first. Okay, so you're always going to choose, your unknown in the numerator is always going to be 1 degree less than your factor in the denominator. 1 degree less. This is considered still linear because it's a product of, it's a power of linear terms. So linear, constant, linear, constant, linear, constant. If you truly have a quadratic or a cubic that you can't factor, this is going to be different now. So if it's a cubic, you're going to have a quadratic unknown. If it's a quartic to the fourth, you're going to have a cubic unknown. So it's always what your unknown you're going to start with is always 1 degree less than the power in the denominator. And this is considered still power 1. because it's power 1 binomial raised to a power. So let's see this in action in the next example. So your unknown that you pick at the beginning, always 1 degree less than the power in the denominator. So here's one. Is it a rational function with the numerator degree less than the denominator? Yes. Degree is 0, degree is 3. Can we factor the denominator? Is it factorable?
Yes.
Yes.
As how? So what can we factor?
X outside.
Yeah, so we take x and x squared plus 4.
Yeah.
Okay, so we're going to do our partial fractions. We only have 2 terms now, x and x squared plus 4. And so what? Linear term, right? Linear term. So we want power 1 less, constant. But now this is a quadratic term. It's truly a quadratic raised to the first power. And it wouldn't matter. It wouldn't matter what that power is. It could be any power. And so since it's quadratic, we need a linear term up here, 1 degree less. So we're going to need bx, but then we also have a constant too. So this is a linear unknown because we have a quadratic term in the denominator. This is constant because we have a linear in the denominator. So always 1 degree less you pick for your unknown. But now the rest is the same. So when our common denominator is the x times x squared plus 4. So what do we need to multiply top and bottom by here to get the common denominator? X squared plus 4. How about the other one? What do we need? X, right? X times top and bottom. And that has to equal what? So we're going to have x squared. So we have 0x squared plus 0x plus 10. So we need, when we add our numerators, we need to get the numerator, which is 10, which means 0x squared, 0x, and 10. So you're going to do the same way. You're going to multiply out. And then we're going to match up, right? A plus B equals 0. C equals 0. That's nice, right? Because that's the only x term, so x terms. X squared terms. And then constant. 4a equals 10. So this one falls out very easily. A is 5 halves. B is negative 5 halves. C is 0.
I have a question.
Yeah, sure.
So in the beginning, had there been a third term that required a linear expression in the numerator, would you also have put plus c or a different variable?
Oh, you need a different variable for every new fraction.
Okay.
Yeah, so we don't want to confuse. This could be different than that, so you need d.
Okay.
Yeah, so if it was like x, you had an x minus 5 or something, then we'd have x minus 5, and then you put d, a new number, so that these don't end up being the same. Trying to force these to be the same when they don't have to be.
So then I can put like a dx plus e.
No, you said a linear term, right? If it was.
Like the numerator would have been linear, not the denominator. Like the denominator would have been like a quadratic.
Another quadratic?
Yeah.
Yeah, if you had another quadratic, say 3x squared plus 1 or something.
Yeah.
And you'd have dx plus e.
Okay, cool.
Yep.
Thank you.
Sure.
Sorry, can you go over really quickly why it's bx plus c again, and not just b?
The unknown in the numerator is 1 degree less than your denominator. Always. So this is the first time we've seen a true quadratic in the denominator. So whenever it's 1 degree less. So if this was cubic, you need to have a quadratic up here, an x squared. This is
I see. Okay.
squared, so you need a linear term. And linear term includes linear and constant.
Okay, thank you.
Okay, yeah, so this is the first time we've seen that. So this is the first time we've seen that you need a bx plus c. So we're ready to do it here. So a is that 5 halves over x plus bx plus c is negative 5 halves x plus 0. So it ended up that the c was 0 after all. Okay, and so how do we do this antiderivative? That's just 5 halves natural log of x. What about this? Negative 5 halves x over x squared plus 4. How do we do that antiderivative? So this is what is essentially the derivative of this, right? This is essentially the derivative of this. So we've got undoing the chain rule, right? Where we're going to do natural log. We're going to have our negative 5 halves. What else will we need to make it the derivative be exactly this?
Yeah.
We're going to need a 1/2, right? When you take the derivative, you get 2x. So we need another 1/2. And I didn't put absolute value here because that's always positive, right? That will always be positive. It wouldn't be wrong to put the absolute value, but you don't need it, okay? X squared plus 4 will always be positive. Okay, questions on this example?
Yeah, I just had one question.
Mm-hmm.
For the bx plus c divided by x squared plus 4,
Mm-hmm.
if the bottom one, x squared plus 4 to the 4th power,
Mm-hmm.
that would still just be the numerator would still just be bx plus c.
That's right. So if this was to any power, this is still considered quadratic, and we still just need a linear term here. But if it was to the 4, then we need a fraction for this thing to the 3rd, a fraction for this thing to the 2nd, and a fraction for this thing to the 1st.
Right.
And we'd have all linear terms on top of all of those. Bx plus c, dx plus e, fx plus g, hx plus I.
Yeah, that'd be long.
Yeah, right. Don't want to do that.
So just to clarify what I just heard, because it didn't click with me for a second. So if this was x squared plus 4, or plus 4 to the 4th power, it's not like it's linear.
What's that? What was the last thing you said?
You would still treat the top like it's
Yes.
linear.
Yep.
So
if you have a power, any powers of a certain degree, it's just considered that degree. Not.
And if it actually said like x to the 4th plus 4x third, blah, 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 then we would do the top being like a tertiary.
Cubic. Right. So if this is if this is to the 4th power, then up here this would be a cubic unknown.
Okay, so the power doesn't matter. The power outside of the
Yeah.
quadratic function.
If you're raising a whole polynomial to a power, that doesn't matter. It's the degree of that polynomial.
Thank you.
Sure. Okay. So that should be enough for you to make progress and do the homework. And for that, the one that's Monday, the undoing the partial fractions. So we want to press on to the next topic, which is more complicated trig integrals. Okay, more complicated trig integrals. So let's do that. Okay, so what's the deal with these? So for instance, the one we'll do at the end of class, I think, is something like 7 secant to the 4th 5x tangent to the 7th 5x. So this is certainly a more complicated trig integral, and hopefully we'll get to this one at the end. So what's the strategy with something like this? Here's the strategy. The strategy is simplify or change the form of the rate function. So we're gonna before we do antiderivative, we're gonna work on this. We're gonna change its form. And there's two ways we can do that. We can just basically use trig identities. Okay, learn your trig identities in pre-calculus, or just algebra and arithmetic. So just simplifying. So by using a combination of trig identities, algebra, we're going to change the form of this to achieve one of two things. Either we're going to get something simple and straightforward, right? So things will cancel out, and it'll just result in a common trig derivative that we know. Something that we can do without a heavy-duty technique. All right? Or we're going to do, changing the form to stage or set up for undoing the chain rule. Remember I said undoing the chain rule is like the most prevalent. It's like the most prevalent technique we see. So you're always on the lookout for it, and it works its way into these other techniques, right? We saw it in undoing the product rule as part of it. We saw it just now as undoing the chain rule or partial fractions. And we're going to actually, that's the goal of this, right? So the goal of these trig ones is to stage, reform this to set it up for undoing the chain rule. Okay, so that being said, let's write down, we need to know our derivatives, right? So those are identities. So sine. Get my pen going here. All right, so what's the derivative of sine x? Cosine x. Derivative of cosine x is?
Negative sine x.
Negative sine. Tangent.
Sec squared.
Secant squared. Cotangent. Negative cosecant squared. Secant x. And cosecant x is negative cosecant x cotangent x. Okay, so remember that our undoing the chain rule, we're looking for something like this. And we're going to recover g of f of x. Right? So we're looking for the derivative of the inside. So here's where these derivatives come in. What we're going to have is g prime is going to be some power of a trig function. Okay? So it's like fx to the nth power. And then we're going to need times the derivative of that. So this is what we're staging for. Some trig function to any power and its derivative using these derivatives. So for instance, cotangent x to the 10th times negative cosecant squared. That would be undoing the chain rule because we'd have any power of cotangent times the derivative of cotangent, we could undo the chain rule. Or secant x to the 8th. What would we need here? So if we could get secant x to some power, then what would we need to have it be undoing the chain rule? Secant times tangent. Or we could have some power of sine. Any power of sine times what? A single cosine. So that's what we're doing here. We're staging, we're trying to get our rate function to be like this with any power of a trig function times just one derivative. We'll be undoing the chain rule, and then we'll have what? 1 over n plus 1 times that trig function to the n plus 1, and we'll be done. Basically, we'll have to clean up the mess, right, like we always do with the coefficients. But this is the idea here. Does this make sense? Does that make sense? So we use identities and algebra to set up a form like this. Some power of a trig function times its derivative, and then that'll be by the anti-chain rule, or the reverse undoing the chain rule will be raise the power of that same trig function. Okay, so let's see this in action. Let's do some examples. So let's look at the we got to look at the identities. So here are the basic identities that you're responsible for. Okay, so hopefully at least half of them are familiar, and there's not too much memorization to do. But your basic definitions of tangent, cotangent, cosecant, and secant in terms of sine and cosine. Your Pythagorean identities: sine squared plus cosine squared equals 1. And then the other two come from that. You can divide all three by sine squared, and you get this one. Divide all three by cosine squared, and you get this one. The half angle formulas are used for, so this is key. Half angle formulas are used for sine squared and cosine squared just by itself. So when you just have sine squared, or you just have cosine squared and nothing else, half angle formula is the ticket, because you can do that's a straightforward antiderivative right there. Okay, and then the double angle formulas. Sine of 2x has one version. Cosine of 2x actually has 3 possible versions. Okay, so let's try an example here. We'll just keep these identities on the screen. Move it over here. Give some room. All right, so the first one we want to do is what's the first one we want to do? Oh, let's do it here. Here we go. What is that? Cosine squared times tangent squared. So we want to use identities and algebra to simplify this. Okay, identities and algebra to simplify this. So what do we notice? What is tangent squared the same as?
Sine squared over cosine squared.
Yeah, and this is very helpful, right? So and there's a lot of trial and error here, because tangent squared is also secant squared minus 1. But secant squared minus 1 isn't going to be helpful here. But tangent squared is sine squared over cosine squared, which is helpful, because then our antiderivative becomes
Sine squared.
just sine squared. And then how do we do just sine squared? Do you remember what I said? Half angle. So this is like, you just have to memorize this. You have to be on the lookout for it. Just sine squared, or you could have a coefficient on x or a coefficient out here in front, but just a solitary sine squared or a solitary cosine squared will always be the half angle formula. You just have to be on the lookout for it to memorize it. So it's going to be 1/2 1 minus cosine 2x. So this is ready to go. 1/2. We just bring the 1/2 out, and then we're going to have antiderivative x, and then it's going to be minus sine of 2x, and we'll need a 1/2 there. Questions on this one? Did you follow? So we used the trig identity tangent squared, which was very helpful in this case because the cosine squareds went away. Then I got sine squared. Whenever you have a solitary sine squared or a solitary cosine squared, you use half angle. So I did the half angle for sine squared. And then I'm ready to do the antiderivative. Antiderivative of 1 is x. Antiderivative of cosine 2x is 1/2 sine 2x.
So will it work to, if we were to, instead of using the half angle theorem, just to say that like sine squared x equals sine of x all squared, and then just use the chain rule?
Will the chain rule work? So you want to do 1/3?
Right. This is an integral, not
Yeah.
My bad.
Okay. Exactly. All right, let's do another example here. There we go. All right, so how about sine 2x times cosine x? Now, one thing that's really important on these problems is you want to have your argument of all the trig functions be the same. If the argument is different, you have a product or quotient of trig functions with different arguments, that's going to be a big roadblock to doing antiderivative. So we want to get all the arguments the same. So what can we do? Is there any algebra or identity we could do here?
The sine of sine 2x is 2 sine of x cosine of x.
Yeah, and this is really good because now we've got every argument is just plain x. So what's that? 2 sine x times? Yeah, so, and I want to point out that this notation is better written so you can see it better. It's always better written like this. You'll see it written like this everywhere. But make sure you know instantly that that's what this means. It means take the cosine of x and then square that. So this is a better way to write it so you don't, make sure you don't get confused. But if you see cosine squared x or sine squared x, this is what it means. Okay, now what? So I've got cosine squared x, and then I have sine x. Anybody see it?
Half integral.
Not half angle. Half angle is only for a solitary sine squared, nothing else multiplied by it, or a solitary cosine squared. Here I have it times sine x. It's not going to be half angle. But what is sine x relative to cosine x? Derivative, right? Therefore, someone said it. Chain rule. All right, so chain rule means cosine x to what power? To the third. We have this 2 coming along for the ride. So we're going to need 1/3 for the 3. Anything else? What is the derivative of cosine?
Negative sine.
Negative sign, a negative that we don't have here, right? Therefore, negative 2 times 1/3 cosine cubed plus c.
I'm just confused at how you were able to just multiply by cosine x.
Where? Up here?
In the second, yeah.
Well, this is the identity. Sine 2x is 2 sine x cosine x. And I also had another cosine x.
Oh, thanks.
Yep.
Yep.
Other questions? The quiz is short. It's very short. It's 2 questions, but it's short. So I wanna do one more example. The hard one I showed you before. Okay, so that last example is this one. 9 secant to the 4th 3x tangent to the 7th 3x dx. Okay, so remember what we talked about. So this one, so what we have, what's the derivative of tangent x? And what's, yeah, so we got these, we've got all these tangents and secants. So this makes us think about tangent and secant. The derivative of tangent is secant squared. And the derivative of secant is secant tangent. So could we stage for undoing the chain rule with this? Meaning, could we get any power of tangent that we want, and then 1 secant squared? If we can get any power of tangent times 1 secant squared would do it. That would be undoing the chain rule. So we're going to pull out let's try that. Okay, so we're going to pull out a secant squared. That's going to be my f prime of x in my undoing the chain rule. Okay. Then what's left is I have another secant squared and my tangent to the 7th.